Okay, this is the last video on the trace determinant plane, and I just want to take a look at one more type of problem. What I've done here is I've created a parametric family of matrices. So the parameter here is A. That's an arbitrary number. This isn't a modeling situation where I'm assuming my parameters are positive. So A can be positive, negative, or zero. This gives me a family of matrices, and so therefore a corresponding family of linear systems. Y prime equals A times Y. And what I want to do is explore the types of behavior that I can get with matrices of this form. And I'm going to do that by looking at where it would fall in the trace determinant plane. Now I can see the trace is just 1 plus 0, so that's always 1. The determinant is 0 minus A, so the determinant is the opposite of A. Now that can be positive, negative, or 0, depending on the value of A. What this does is this gives me a parametric curve in the trace determinant plane. Now when I think parametric curve, I usually think x and y are both functions of t. Here, t and d are both functions of A. This is just a particularly simple curve because t is a constant function. It's always 1. So that would give me this line over here, this vertical line, t equals 1 in the trace determinant plane. And if I look, I can see that there are 1, 2, 3, 4, 5 different types of behavior that we can get. So what I'm going to do is I'm just going to mark off a point in each of those regions. Okay, so here's B. I'm going to start with B because I used A as my parameter. C, D, E, and F. I'm actually going to start with the point at E. E is on the t-axis, which is one of the critical loci. That's a vocabulary word that I don't think I've used yet. The critical loci are the t-axis, the positive d-axis, and this parabola. They're the curves where if you cross the curve, the behavior radically changes. The type of phase portrait that you're getting changes. Okay. What's neat about being on a critical loci is that I can actually figure out exactly what A value puts me there, and then I can figure out the exact phase portrait. So I'm not just sort of coming up with, in general, this is the sort of thing I have, but this is exactly what I have at that point. Notice that at that point, T is 1 and D is 0, so that means that A is going to have to be 0. So the matrix that we're talking about in this case is 1, 1, 0, 0. Okay. Now, I've written up here the general characteristic equation that we get in terms of the trace and determinant, and then just use the quadratic formula to solve for the roots. So in this case, I don't even need to know what the matrix is. I can just plug in T and D. Lambda is going to be 1 plus or minus the square root of 1 minus 0 over 2. So lambda is going to be either 0 or 1. So with 0 as an eigenvalue, we're going to have a line of equilibrium solutions. And with 1 as our other eigenvalue, the other solutions are going to be lines moving away from an equilibrium solution. But I can figure out exactly what those lines are because I do have exactly this matrix. So if I look at finding, let's say, an eigenvalue for 0, I'd be looking at A minus 0i times V1, V2 has to equal 0. But that's just A times I, 1, 1, 0, 0. Sorry, A times V1, V2 equals 0. The corresponding equations are V1 plus V2 equals 0. And the lovely next equation I get is 0 copies of V1 plus 0 copies of V2 is equal to 0. Now obviously that second equation is satisfied by all V1 and V2, so this is just telling me that V1 is the opposite of V2. So for lambda equaling 0, I'll say lambda 1 is 0, V1, I'm just going to choose V1 to be 1, and that'll make V2 negative 1. So I found a specific eigenvector for that eigenvalue. Let's do the same thing for our second eigenvalue, which we said was 1. So if lambda 2 is 1, A minus I times, I'm just going to use W's here, W1, W2 has to equal 0, 0. But that's just subtracting 1 from the main diagonal. So I'll get 0, 1, 0, negative 1. W1, W2 has to equal 0, 0. Nothing plus W2 has to equal 0. Nothing minus W2 has to equal 0. That's telling me W2 is going to be 0. But W1 is free to be whatever I want. Okay. So my second eigenvector, I'm going to call it V2. I was just using W's here to avoid reusing V1 and V2, although it's totally fine to recycle the names of your unknowns. So I'm just going to choose 1, 0 here. But now I can draw the specific phase portrait that I get at point E. So I'm going to have a line of equilibrium solutions that corresponds to the vector 1, negative 1. So there's my line of equilibrium solutions. My other solutions have to be parallel to 1, 0. So 1, 0 would just point straight to the right. So my solutions will point straight to the right if they're a positive multiple of that, or straight to the left if they're a negative multiple. And because lambda 2 was positive, they've got to be moving away from an equilibrium solution. Not necessarily away from the origin, although the solutions on the x-axis certainly will. So there's my phase portrait at E. Let's take a look now at C. That's the other place that, since it's on one of the critical loci, I can actually find the exact matrix, the exact eigenvalues, and therefore the exact eigenvectors that I would have in that particular case. Okay, so if we're at point C, I know that we are on this parabola, but the parabola is where this discriminant here, t squared minus 4d, is equal to 0. So I know that t squared minus 4d equals 0, but that's 1 squared minus, actually plus 4a is going to equal 0. Yes, d was negative a, so minus 4d is plus 4a. So that's going to give me 4a is equal to negative 1, a is negative 1/4. So I now know that my matrix is 1, 1, negative 1/4, 0. Okay. Notice we're here if a is equal to 0. We're here if a is negative 1/4. That's consistent with the fact that I said that the orientation was going to be downward. Now, if I look here, my eigenvalues are going to be, I'm just going to plug in, let's see, so t is 1, d is now positive 1/4, okay, because it's the opposite of a, and a is negative 1/4. So lambda is going to equal 1 plus or minus the square root of 1 minus 1 all over 2. So lambda is equal to 1/2. That's the only eigenvalue we have. Well, that makes sense. I remember that on this parabola, that's the boundary between this being negative, this being positive, and that boundary would be where this is 0, but that's going to mean that we have a repeated root. Ordinarily, when I know I'm on that parabola, I don't have enough information to know whether I'm in the situation where I've got 1 independent or 2 independent eigenvectors. But in this case, I do know, or at least I can figure out, because I've got this matrix. So I'm going to look at a minus 1/2 I times v1, v2 has to equal 0, 0, so that I can get myself an eigenvector. So I'm subtracting 1/2 from the main diagonal, so I'll get 1/2, 1, negative 1/4, negative 1/2, v1, v2 equals 0, 0. So my corresponding system is half of v1 plus v2 equals 0, a quarter of v1 sorry, negative a quarter. Spaced for a moment, I didn't see that negative sign there, and it wasn't working out. Okay, negative a quarter minus a half v2, negative a quarter v1 minus a half v2 equals 0. That is a dependent system because this is just negative 1/2 times this. So that's basically telling me that v2 has to equal negative 1/2 of v1. So I'm going to just record that my lambda was 1/2. I'm going to choose my corresponding eigenvector. I'm going to just put a 2 for v1 so that when I multiply by negative a half, I get negative 1. So I can see that I only get one independent eigenvector. So we're not in the case where every non-equilibrium solution is a straight line solution. We're in that case where our solution curves that aren't straight line solutions are trying to spiral and failing. Okay, so let's draw our line of equilibrium solutions. That corresponds to my vector 2, negative 1. There's not my line of equilibrium solutions, my straight line solutions. My equilibrium solution is at the origin, and because lambda is positive, these solutions are moving away from the origin. Now, I want to know, I know my solution curves are trying to spiral. I want to know in what way they're trying to spiral. I'm just going to plug in, I think, 0, 1. If I look at 1, 1, negative 1/4, 0 times 0, 1, I'm going to get 1, 0. Remember, the shortcut is that when you put the 1 in the second position, you just get the second column of the matrix. So at the point 0, 1, we're trying to move in this way. The solution curve is coming like so. So that corresponds to trying to spiral clockwise. So we're moving away from this equilibrium solution. We're trying to spiral, so I got to be tangent here like so, but we can't quite spiral because we're going to get blocked by this line. So my phase portrait would look something like so. Now, I could, for B and D and F, pick a specific A value and come up with a specific phase portrait. I can see now that if A is smaller than negative 1/2, we'll be up here between, negative a fourth. Between negative a fourth and 0, we're in this region, and when A is positive, we're down here. In the interests of time, I'm just going to very quickly draw a representative phase portrait for the regions that we're in. If you're asked in homework, on a quiz, on an exam, to do one of these things, make sure you read the directions carefully. If you're asked to pick a specific value of A and draw the exact phase portrait that you're getting, make sure you do that. If you're asked to just say draw a representative phase portrait for the region that you're in, that's okay. But make sure you do what the directions ask. Okay. So for B, we're up here in the region where we have complex eigenvalues, but our T is positive. That's going to be making the real part of our eigenvalues positive. So that would be a spiral source. If I chose a particular value of A, I'd know whether it was spiraling clockwise or counterclockwise. Down here at D, we've got two real eigenvalues. They're both going to be positive. And they're basically both positive because here D is positive. So here I'm subtracting something from T squared so that this square root is smaller than the absolute value of T, which is just T. So that T plus the square root is positive. T minus the square root is still positive as well. Okay. And I know in this situation, basically, so let's see, we're moving away from the origin. I would start roughly asymptotic to one type of curve and end almost parallel to the other straight line solution. Okay. And then F, that was where we had a saddle, because I would have one negative and one positive eigenvalue. Now, if you don't remember that, you can always figure it out really quickly. Okay? In this case, my t is 1, my f would be some positive value. So I can see that t is still positive, but if d is positive, that's going to mean that t squared minus 4d hang on a second. Oh, I'm sorry, d is negative. T squared minus 4d becomes bigger than t squared. So when I'm subtracting this from here, this piece is bigger than t, so that would give me something negative. Okay. So that's just a very quick representative phase portrait of the types of things I have at B, D, and F. Again, make sure you're reading the directions if you're asked to pick a particular value of A and draw the phase portrait for that specific matrix. Make sure that you do that.